Okay, good afternoon. My name is Gautam, and I'd like to talk to you about replay debugging data center applications. Now, this work was done jointly with my colleague Dennis Gield, who is now at Google. He graduated a while ago, and my advisor Jan Stojka. Okay, so where does this project fit in the RAD Lab architecture? Well, it fits in at the very bottom of the cluster software stack. Our project is called DCR. And this is what this talk is going to be about. Okay, so what exactly is this talk going to be about? It's about debugging. We all know it's hard. But more specifically, it's about debugging data center software, which is really, really hard. Now, what do I mean by data center software? I'm talking about large-scale, data-intensive distributed applications like Hadoop MapReduce, HDFS, GFS, Bigtable, HyperTable, HBase, so on and so forth. Why is it hard to debug these applications? Well, the key reason, one of the main reasons, is non-determinism. You write this application, you deploy them in production, something goes wrong, but then when you try and reproduce the problem in your development environment, you can't. And now because you can't reproduce these problems, you can't reproduce the failure, then you can employ traditional cyclic debugging techniques to repeatedly run the program in order to home in on the root cause of the failure. So in this talk, I want to focus specifically on the problem of reproducing non-deterministic failures in data center software. So how do we do this? Well, the overall approach is that we leverage deterministic replay technology. And the basic goal of this technology is to generate an identical replica of some original program run, and hence the failures in that run. Now, briefly, this works in two phases, a record phase and a replay phase. During the record phase, the deterministic replay system logs or records non-deterministic data such as incoming packets, inputs, keyboard presses, interrupts, so on and so forth, to a log file. And then later, when you want to reproduce the bug, the failure, then you initiate a replay session, at which point the application is re-executed, but this time the non-deterministic events from the log file are used to drive the replay execution. Now, at this point, you're probably wondering why did we choose deterministic replay? Why not use model checking, testing, and verification to find the bugs before they show up in production? Well, as good as these tools are, they aren't perfect. They often miss bugs. And when you're talking about difficult applications, large-scale data center applications with large state spaces, then they can miss a lot of bugs. And when that happens, these bugs fall through into production. And at that point, you will want deterministic replay to reproduce those production bugs, to figure out what actually went on. So deterministic replay technology is complementary to model checking, testing, and verification. Okay, at this point, I'll step back a little bit, and I'll tell you that the problem of deterministic replay in data center software is very hard. We've been at it for quite some time now. Our first generation system, was called liblog. And it was geared toward the Planet Lab environment. So liblog could replay large-scale distributed applications, but it was for Planet Lab, a very low I/O intensive environment. Okay, it's not the data center. Following liblog, we built the Friday distributed replay system, which was really an improvement of liblog in that it provided higher-level debugging facilities on top of the replay infrastructure. So, for example, it provided things like global invariants, distributed watch points, distributed breakpoints. But still, Friday was inadequate for the data center. For one thing, it inherited liblog's limitations, no I/O-intensive applications. And second, it didn't have multiprocessor support, which was becoming very important in the data center. And soon after that, we worked on, we made the next step, and we moved to the output deterministic replay system, in which we added multiprocessor support. So now we could actually record efficiently those applications that use multiple processors. However, ODR still performed poorly on I/O-intensive applications. So you couldn't use it on Hadoop jobs or HyperTable, any kind of terabyte scale computation. Okay, so I've told you data center replay is hard. So what exactly is the challenge? What's been holding us up? Well, it turns out that there are three requirements, and any kind of data center replay system must meet all of these requirements simultaneously. For most, the most important one is that the system should record efficiently. Okay, we're talking about to be used in production, it has to be less than 10% slowdown and 100 kbps per node logging rates. The second requirement is that the system should be able to replay the entire distributed system if the user so desires. The reason for that is that you have no idea beforehand on which nodes a bug is going to manifest. It could be on one node, two nodes, or it could span the entire cluster because we're talking about distributed bugs. And finally, a replay system should be practical, right? It should work out of the box. It should work on x86 machines. It shouldn't require non-commodity hardware. It shouldn't require special languages or APIs that ultimately limit the applicability of the system. Now, if you look at the related work, apart from ours, in this area, you'll see that there are many systems for deterministic replay, but all of them fall short in one category or the other when it comes to data center scale workloads. There's extremely I/O, large quantities of data. So VMware Workstation, a commercial replay system, you can do whole system replay out of the box use on VMs. However, according to our experiments, data center scale workloads, it performs poorly, over 2x. IBM Deja Vu is a very old replay system. It can actually record efficiently, but it assumes a closed world. And the data center is actually open. There's inputs coming in from the outside, from users. And so when that happens, the system cannot guarantee replay. And then finally, there's more recently the Microsoft R2 system. It can record efficiently and can provide whole system replay, but it requires a special annotation language that you have to kind of retrofit your applications to use it. And so it's very challenging, especially when it comes to multi-processor data races, which are hard to annotate because you don't know where they are. Now, so what is our contribution to this? Well, we're working on DCR. It stands for a data center replay system. And you can use it to replay debug your data center software. Now, the novelty about this is that we can actually meet all three of these requirements. We can record efficiently. We can provide whole system replay. And the system works out of the box. It's designed specifically for Linux x86 and for the EC2 environment. And again, it's for large-scale data intensive distributed applications, Hadoop, HyperTable, HBase, so forth. Okay, so we built a system, but what was the key insight that enabled us to meet all of these requirements? What was the gist of our basic approach? The key intuition behind the system is that for debugging purposes, we don't need a precise replica of an original program run. It oftentimes suffices to produce some run that exhibits the same control plane behavior. So control plane behavior, what do I mean by that? So if you look at these data center applications, you can divide them up, the code of these applications, to two components, the control plane code and the data plane code. Now, the control plane code is kind of the brains, the administrative component of the system. It manages the data. So it does things like distributed data placement, maintaining replica consistency, and it tends to be complicated. It accounts for 99% of the code, according to our measurements. But at the same time, it accounts for just 1% of the overall I/O traffic. Now, this is in stark contrast to the data plane code, which is actually the workhorse of the system. It's responsible for processing data. It tends to be simple and high traffic, so it does stuff like checksum verification, string matching. In other words, operations that scan each and every single byte and perform some computation on them. Now, in contrast to the control plane, the data plane tends to be pretty simple. It accounts, by our measurements, to just 1% of the code, but at the same time, it accounts for 99%, sometimes more, 99.2, 99.6% of the traffic in the system. Now, here's the most important part, that our observation is that most failures stem from the control plane component. Okay, because it's the most complicated. It accounts for the most code. Okay, so where does this insight take us, this whole control plane, data plane dichotomy? Well, now, what this allows us to do is that we can now relax determinism guarantees. In other words, we can shoot for control plane determinism. That is, which is the idea that, okay, it suffices to reproduce some execution that exhibits the same control plane behavior. Now, if we can do this, then we can altogether avoid the need to record the data plane, which is the most I/O intensive. It accounts for 99%. And by doing this, we can actually record efficiently at such large scale. So, and as a result, we can meet all three of the requirements because we don't have to make trade-offs that typically been necessary. Okay, so, oh no. Okay, so, all right, so that was the approach. That was an overview of the system. Now the question is, does it work? What do we have to show for all of these years of work? And we have a demo for you of DCR in action. Now, okay, so in this demo, we have two goals. The first goal is simply to show that, okay, we can replay real data center applications. And in order to show this, I'm going to demo replay an execution of Mesos for you. Now this execution was collected on EC2 and 32 nodes. Now we'll replay that for you in the first part of the demo. And then in the second part of the demo, I will show you that DCR goes beyond mere replay. That is, in fact, also a powerful debugging platform on which you can build interesting debugging tools and analyses. Okay? And to demonstrate this, I will show you one particular analysis that can be very helpful in finding that proverbial needle in the haystack. Okay, so for part one, we're just going to show you that, okay, we can replay Mesos, which is our in-house cluster operating system. First of all, our replay system is deterministic, and one way to see that is that it reproduces the same outputs. So if you look in the second projector, what you're seeing here is a replay, the replay in progress of the data center DCR. And what's happening here is that Mesos is starting up, the master is started up, and then soon you'll see the slaves starting up, and then you will see them communicating, sending heartbeats, and then they're going at it. Okay? So this will go. So this just this basic deterministic replay. Now, of course, looking at the outputs alone is not usually sufficient for finding bugs, to isolating root causes. Sometimes you want more information, more fine-grained information, and DCR can provide that kind of information for you as well. So to see this, what we have here is a demo of DCR providing an instruction trace, which is collected during replay of the distributed system. So this is an example of an expensive tracing operation that you can do during replay, but would be normally prohibitive in production to collect. So this is a simple instruction trace that shows, okay, Mesos master is starting up, it's executing code in the dynamic linker, and these are the functions that is currently executing. Now, an instruction trace, as nice as that is sometimes too much information. It's too detailed. Sometimes when you're talking about distributed bugs, you want the bigger picture. You want a bird's eye view of the distributed system. And DCR can provide that as well. And here, you see a bird's eye view of the distributed system of Mesos replaying. And what you're seeing is on the left panel, the set of all active threads in the distributed system. On the right panel, all the active communication channels between nodes, sockets, pipes, files, named pipes, so on and so forth. And in the bottom two panels, you'll see the messages that are in transit, that have been sent but not yet received. And then finally, the messages that have been received. Let's see if I can move this up. It's just started to kind of ramp up. I don't know if you can see this, but an important property of this replay is that it's consistent. You're not going to see a message received unless it has already been sent. So this is a very important property. This causality property is necessary in order to reason about bugs. Okay, I'm going to pause that. I'm going to move to the second part of the demo. Okay, I just showed you that, okay, the basic operation works. Now, the question is, how is this useful for debugging, right? I mean, replay, okay, fine. That's nice. You can look at it. But how does it help all of us in debugging? Well, the nice thing about DCR is that it's a platform for building analysis tools. What that means is that you can build these tools, things like global invariant checkers and data race detectors, symbolic execution tools, and distributed data flow analyses on top of the replay infrastructure. So you can do these expensive analyses that you normally couldn't do in production. Now, the other point that I want to make about this is that writing these tools is actually very easy on top of this infrastructure, and that's for three reasons. Foremost, DCR provides a global yet centralized view of the distributed system. much like that of a network simulator. So you aren't, in order to write these tools, you don't need to do distributed programming. You have global state. Secondly, the replay is causally consistent, as I demoed earlier. That means that you don't have to worry about collecting consistent snapshots, which requires typically sophisticated algorithms. DCR automatically ensures consistent snapshots for you. And finally, DCR provides an easy-to-use language, Python. Basically, you can write your tools in Python. That makes it really easy, really fast to develop these analysis tools. Now, for this demo, I want to focus on one of these tools in particular, our distributed data flow analysis tool, which we call DDFlow. And this tool basically dynamically tracks data that you designate through the distributed system. Okay, so what this means to you is that you give it a file to be tracked, and then it will basically tell you all of the functions that a node, all the functions that operate on that file's contents by one node. But beyond just one node, it'll track this data across messages to other nodes as well. So it does intra-node tracking as well as inter-node tracking. And this particular tool that I'm going to demo was written in just 100 lines of Python code on top of our DCR replay infrastructure. Okay, so is DDFlow useful? Well, let's consider an example. A data loss from HyperTable. Find a better spot for this. Okay, so let's consider a bug from HyperTable. In this particular bug, the user inserts data into a table, but then when he does a subsequent lookup, he can't find that data anymore. It's lost for some reason. And then at that point, the developer wants to know, okay, why is it lost? Now, I'll tell you up front that the cause is a race in the way HyperTable does table migration. When a table gets very large, it splits the table and then moves it over. But then if there are writes that are pending, a race causes some of those updates to go to the wrong shard of the split. And as a result, subsequent lookups go to the wrong shard, and then it just becomes inconsistent. And you don't get the data that you see. So how does DDFlow help? Well, we can run it, and we can see. So here we have DDFlow running, distributed data flow trace, and it's basically running, and it's giving you a trace of the data as it flows through the distributed system. And I'm going to stop it right here. I think that's enough. Well, what you can tell from this is that the data is first loaded by the client, which is node ID 2 in this particular run. And you can see that it's loaded because it invokes the load data source function. And after some processing, it's sent finally to node ID 1, which is the range server, the server responsible for maintaining the table data. And there it's inserted into a red-black tree. So now at this point, you know what the problem is, because the lookups, based on your inspection of the log, went to node 3, yet the data that you inserted is now going to node 1. So clearly there's an inconsistency, and now you've saved yourself some time poking through the debug logs. You can try and figure out exactly where that inconsistency came about. Okay, so that was the demo. Hopefully I've convinced you that DCR is a powerful platform. And so does this mean that the problem of data center replay has been solved? Well, unfortunately not, okay? And this is a very hard problem, and we are still working on it, and there's many things to work on. One of the most important limitations of DCR is that it has a really long time to replay. From the moment you're done with recording and the moment that you can start replaying can be very long. So it can be as high as 60x. So for a one-day recording of IO-intensive, data-intensive computation, that could mean you have to wait 60 days before you can start the replay. Obviously, that's not useful in all cases. So, you need higher turnaround time. And the question is, why does this happen? Well, it's because rather than record data plane inputs, DCR tries to compute it using sophisticated program analysis techniques, which basically amount to a search problem. And on top of that, you have to search through the program through multiple paths, and then there are hash functions you have to deal with. So it's basically a very hard search problem. That's why it takes so long. Now, is it completely hopeless? We don't think so. So one of the key observations that we've made is that in applications like MapReduce, the data plane inputs are often persistent. Okay? So let's take the example of a MapReduce application that tallies clicks from a click log. The data plane inputs in this case would be the click logs, the data that's being processed, and it's terabytes of this stuff. Now, it's usually kept persistent. It's kept in some distributed file store because sometimes the MapReduce job is written incorrectly or something goes wrong and then the data has to be processed again. But we take advantage of the fact that the data is there as part of the application execution, and then we can simply reuse it. Hence, we can avoid the need to record and post-compute it altogether. So that's a very promising approach that we think can reduce the time to replay. And with that, I'm going to conclude with just a basic wrap-up. And it's that control plane determinism, our key insight, can enable record-efficient data center replay and a powerful high-level analysis. But at the same time, we need to work on speeding up the time till replay. And at this point, I'll stop and I'll take your questions. Question?
So how do you take an inherently non-deterministic distributed application and make a deterministic recording of it? Do you require that your applications be serializable before you can actually record and replay?
No. You just basically record non-deterministic inputs. There are many sources of non-determinism. Inputs from the keyboard is a classic example, but also incoming messages from the network. And then you have multi-processor non-determinism, interleaving of instructions across different cores. There's communication on shared memory. So all of these things have to be captured precisely in order to guarantee determinism.
So do you need synchronized clocks in order to make sure that your recordings on different machines can be lined up?
No. So we don't assume synchronized clocks. We use logical clocks. So our replay there isn't perfect. We replay in logical time. So the basic criteria is that if the replay system says you've received a message, then some other node during replay should have sent it.
Okay, so you have to instrument all network communication with logical clocks then.
Exactly, yes.
Okay.
Yes.
Can I ask another question? What would you do if, how would you change your system if you had a lot more recording bandwidth available to you? Is there a threshold over which you can record the data plane, and do you get more? Because I'm imagining we could put flash drives in computers, or we could record by streaming off data to other computers in the same rack or something and get a lot more than the 100 kilobits you gave yourself.
Yeah, so I guess you could increase the data rates, but there's still a lot of overhead in terms of copying that information to a log. So even if you use flash drives or better storage technologies, that would undoubtedly help, but that wouldn't eliminate the problem. You'd still have to do a lot of copying. And then there's storage issues, because you're talking about you have dedicated storage for terabytes of data, and then now on top of that, you want to have a copy of that data. So you need twice the amount of storage and twice the amount of storage infrastructure. So there's the economic impact in terms of the costs of storage. You'd have to invest in more storage.
I'm just imagining if your program is important enough, you could imagine building a second cluster just to get the darn thing working.
Sure. Well, yeah. So I guess that would, So I guess we would have to find such an application. Traditionally, people haven't been willing to kind of use these tracing tools and leave it on all the time. I guess they don't think that it's valuable enough. But I guess that's probably one of our missions, to kind of convince people that you can do really cool stuff if you have this infrastructure. And then it might actually be worth the cost. Yeah.
Have you thought of combining this with compression schemes? For example, you see the same sequence again and again, and you can compress those?
So with respect to the data plane inputs, we've only done kind of very simple compression. So we just run gzip on it periodically as we log it, but nothing more sophisticated than that. We've done more sophisticated compression schemes in prior work related to multiprocessor replay, and I can talk to you about that offline, but that has to do with compressing branch traces. But that's certainly one thing that could help. But there is a cost to compression as well. So I mean, you incur CPU overhead if you do it. So it's not really clear to me if it's worth it. It might not be worth it in all cases. So.
Okay, are there any more questions? Okay, then I guess it's time for a break.